Okay, hello, grade 11 student. Welcome to our new video. In this video, we will solve a question from past paper 2023, three response questions, set 2. Now, let me remind you that our target is to solve questions that are related to chapter 7. The equation that you would use for chapter 7 are these set of equations. Among of these equations, you should memorize some relationships that are related also to this lesson, such as the equivalent springs or the equivalent spring constant, and other things. You may find them in our PowerPoint. Now, today, as I said, we will solve only one question, question 2. Now, a student conducts an investigation to determine the relationship between the period of oscillation T of a system consisting of a block and an attached spring. The student starts with a block of mass M attached to a single ideal spring. What does it mean by ideal spring? Ideal spring means this spring obeys Hooke's law, which means the omega equals K over M, and the period that we found them in the table of information are valid in this situation and no need to provide any proof in order to use them. We can use them directly. Now, as shown in figure 1, let's break down the figure 1. This figure 1 is consist of only one ideal spring, one mass, the hand to release the object from rest, and the motion detector. Now, the motion detector is used for different things. One of these things that we can use it for is to measure the T, the period. Okay, let's complete. The student holds the block so that the spring is neither stretched nor compressed. At a vertical height 1 meter above a motion detector, the student releases the block from rest and records the period of oscillation for a system consisting of single spring and block. An additional identical, we have identical springs, so the same K is attached in parallel as shown in the figure 2. So in figure 2, what do we have here? We have same mass, same spring, but now in addition to this spring, we have another spring with the same K and a motion detector below. Now, and the procedure is repeated for n is equal to springs, as we saw. This procedure is repeated through n is equal 10. Let me remind you that the n here represents the number of springs. So we repeat the same measurement with the same mass and the same identical springs, but with 10 springs, up to 10 springs. Derive an expression of t as a function of n. Express your answers or your answer in terms of mass, spring constant, n. So I don't want to see numbers here. I need to plug values instead of nk and m. I must see in my equation the following terms with the physical constant. Now, when I say physical constant, I mean by physical constant, it can be g, for example, the gravitational acceleration. Now, let's start with something essential here that link the T with the mass K and N. This thing is known as the period of the vertical oscillator as well as the horizontal. Now, T pi radical M over K is valid here. No need to provide any proof regarding this relationship. Now, the mass is the total mass of the system, and the K is the equivalent K of the system. Now, we know that according to the figure 2, that the 2 springs or the 3 or the 4, whatever the number of springs are, the springs are connected in parallel. And we know that whenever we have parallel combination of springs, we can combine them to form the equivalent K Let's call it equivalent. So this is the equivalent. So K1 plus K2 plus K3. But since we are working with identical Ks, so let's replace them with the same notation, which means the same value. Now we're going to add all the Ks up to n, or we can rewrite our equation such that n times k, because we have n numbers of springs, so we multiply this n number with k, the spring. And in this way, we can find the equivalent k. So let's substitute it in our equation. N, k, this is our relationship in terms of n, in terms of n, in terms of k, and the physical constant. Neat. Let's keep moving. We have a long journey today. Now, on the following axis, sketch a graph of t as a function of n for n greater or equal than 1. So here in this question, they want me to start from number of springs, which is equal 1, which means we have only one spring, and above. So the sketch should start from 1 and above. This sketch will allows me to indicate the behavior of the spring or of the period as the number of springs increased. Now let's get back to the equation that we have derived. T is equal to pi n times k. The thing is, here the sketch represents the variation of the period in terms of n. So we can rearrange this equation such that the n is completely isolated from this fraction. To do that, I must write t is equal to pi, the m over k alone, and let's separate now the n from this part. Now the n can be written as 1, and here since the n is included in the radical or the square root, so I must see this, the square root with it. Now as we can see, this relationship, it's a relation between t and n. Now, this does not represent a straight line because it's inversely proportional. So t is inversely proportional with n, which means we should expect that as the n increases, the t decreases according to this relationship. Whenever we have something in the denominator with relevant to t, then they must have inverse proportionality. How we can draw the inverse proportionality? We just start from a certain value, and this value start to decrease in non-linear way. Yes, that's it. Now, let's move on to the next question. The student plots the data for t squared as a function of n minus 1 now. N minus 1, it's similar to say this is 1 over n. As shown in the figure, draw the best fit line for the data. Now, to draw the best fit line for the data, okay, we need to draw a line that best fit through all the points. And this best fit line can be drawn like this. Okay, so this one would be sufficient. Let me correct its location first. Okay, so this is our best fit line. Don't forget, you must use a ruler here to draw the best fit line. Now, let me remind you, whenever we have a straight line, in the graph, remember that this graph holds features. One of these features is the slope. So think about the slope for the next question. And remember that the slope is equal rise over run. To calculate the rise over run, you must have 2 points to complete the solution. So let's see what do we have in the next question. The mass of the block is measured to be 1.5 kilograms. So we have the mass of the block now. Using the graph, calculate an experimental value of the spring constant K for a single spring. So only for a single spring, we need to know what will be the K. Now, to do that, we should recall the formula that we got. The T is equal 2 pi m over k multiplied by 1 over radical n. Now the thing is here we must see t squared in terms of n minus 1 or 1 over n. So let me modify the equation in order to obtain the t squared and 1 over n. Now if we square both sides, we must apply the squaring here, and the squaring there. Everything should be affected under the square. Even the 2, the pi, the radical mk, and the 1 over radical n. So we will get that the t squared is equal 4 pi squared multiplied by m over k. So the square will destroy the square root. The square will be applied on pi and 2. It becomes 4 pi squared. And for here, the square of 1 is just 1. And the square of 1 over radical n is n. So let me write it again. So 4 pi squared multiplied by m over k. These all are multiplied by 1 over n, which is just the n minus 1. We can write it as n minus 1. Now, this equation is similar to the linear equation that says y is equal the slope multiplied by x, where the b here is equal to 0. So we can say that the slope is just the 4 pi squared m over k. So if I know the slope of the graph, the best fit line, I will be able to equate the slope from the graph with the 4 pi squared m over k. By solving this equation, I will be able to find the k. So let's complete by finding the slope. Now, to find the slope, we just need to apply the rise over run. For that, I will choose 2 points. For example, I will take this point. Let me remind you that we don't take the point that are represent the data, the collected data. We take our point to calculate the slope from the line itself, not from the data. Be aware. Now, for this point, which is belong to the line, it has the following coordinate. So it's 0.3, and so this here, this is 2, 2.5, 3, 3.5, and 3.5. And for the second point, I prefer to take this one. So this is 10, 10.5, and 0.1. So 0.1 and 10.5. Now the slope is equal 10.5 minus 3.5 over 0.9 minus 0.3. Plug and chug, get the value, and the value for the slope is equal 11.67. It's important to mention the unit used. So let's evaluate the unit for the rise and the unit of the run. So vertically here, the unit is squared, So this is S squared. And horizontally, as we can see here, there is no any unit because this is just number of springs, so it's unitless. This is why the final answer should be second squared over 1, which means this is second squared. Now, we have the slope, and we know that the slope is equal to this relationship. So let's replace the slope with the corresponding value. And don't forget that it's equal to the 4 pi squared mass over k. Now, by solving this equation, where the subject here is k, the m is given by 1.5, we will be able to find the k, and the k is equal 4 pi squared mass, which is 1.5, according to the given in this part, over the 11.67, and use your handy-dandy calculator to get the answer. The answer must be 5.70 or zero 0.7 Newton per meter. This is the SI unit of K. Neat. What next? The student finds that the value given by the manufacturer for the spring constant is larger than the value determined experimentally in part C. So we found that the value of the spring that we got it here, which is 5.07, it's much larger than the value provided by the manufacturer. Determine a single source of experimental error that could result in the observed difference in the value of K. Briefly justify your answer. Let me remind you that we have calculated the value of K based on the period, and the period is given by 2 pi m over K. Now, here in this experiment, we found that the K is larger. As the K increases, the T decreases, according to the fact they are inversely proportional. Not like the mass. The mass is directly proportional. Let me remind you that by drawing this line, any quantity that's above this line, directly proportional, below this line is inversely proportional, and indeed K is inversely proportional with the period, or at least the radical K. Now, how did we find the T? Actually, we didn't find it. We didn't calculate it. We just measured it using the motion detector. So maybe there is a problem with the motion detector itself that makes our measurement incorrect. So in my answer, I should say following should relate it to the motion detector. Most probably it is due the miscalibration on the motion detector that produces a graph with a larger period. Sorry, it's a smaller period. Sorry. Let me read it. Manufacturer for spring constant is larger than the value. So the manufacturer has, so our value is smaller. So the period is equal to pi radical m over k. So the k is smaller, the period is larger. So definitely the period that we got is larger. Okay. So let me correct it with a larger period that gives a smaller value of K needs. Now, let's keep moving. Almost done. Now, the student conducts a similar investigation to determine the relationship between the period of oscillation of the system or of a system consisting of block and the number n of identical springs, but arrange the block spring system horizontally instead of vertically. So we maintain the same experiment, however, we change the configuration of the system. Instead of having the spring with the mass horizontally, we place them, sorry, it was vertically. Now we place them horizontally according to figure 3. There is no friction between the table and the block. In each trial, the block is displaced the same horizontal distance from equilibrium and released from rest. The student plots t squared as a function of n minus 1 for this new data. Would the slope of the specified line from this new investigation be greater, less, or the same as the slope of the specified line in the part C? First, I should to add tick on one of these answers, but let me remind you that vertical and horizontal oscillator, in the absence of friction, they will obey the following formulas. Since we didn't change the mass, we didn't change the K, then we will get the same period over and over again, which means the slope that we will plot or we will get will be exactly the same as the slope for the vertical one. So the same. Briefly justify your answer. Now, the period here, the period for both horizontal and vertical oscillators is given by T is equal to pi square root m over k. And both m and k stay the same. Then the slope of the best fit line, BFL, is the same. Expected. Now next. This is the last question. When n is equal 1, the maximum speed of the block is found to be Vmax. When we increase the number of n, will Vmax increase, decrease, or stay the same? Let's find out. Now, the Vmax has a specific relationship. This relationship, it doesn't in the equation sheet. So it's omega times the amplitude, where the amplitude is just the x max. Now, the omega is radical k over m times the amplitude. So the Vmax has something to do with the k, with the mass, with the amplitude. However, here we change the number of springs and we made them n. So let me add here nk. So what happened to the k, the total k in this case? It will increase. And according to this relationship, there is proportionality between the Vmax and the k. If we increase the k, the Vmax will increase. Let me draw the line now. So k and n are above the line, which means they are directly proportional with V. So what will happen to the V? It will increase. Now let's justify. We just need to write the relation that link the K with the Vmax. So as K increases, then Vmax increases. That's it for today. See you in new video soon. Bye bye now.